Team Isotech, and this is our select video presentation on the production of bisphenol A, aka BPA, from cumene. We'll start by looking at the Aspen process simulation. We separated our process into three key sections: cumene oxidation, cumene hydroperoxide, aka CHP, decomposition and separation, and BPA production. Section 1. Cumene oxidation. In this section, cumene and air are fed into the process at 25 degrees Celsius and 1 bar. The cumene stream is pumped to 5 atmospheres, whilst the air stream is mixed with the cumene recycle stream and also compressed to 5 atmospheres. The streams are mixed and cooled to 110 degrees Celsius and then fed to the oxidation reactor, which produces CHP at approximately 30 weight %. An expansion valve is used to reduce the CHP effluent stream to a pressure of 0.02 atmospheres, and it is then fed to a vacuum distillation column operating at 90 degrees Celsius, where it is concentrated to approximately 80 weight %. The distillate stream consists of unreacted cumene that is compressed and sent for further processing before being recycled, whilst the concentrated CHP is cooled to a safer temperature of 70 degrees Celsius and pumped onto the next section.
The second section of the process simulation consists of the CHP decomposition and the separation of acetone, AMS, and phenol into separate streams. The concentrated CHP from the vacuum distillation column in section 1 is fed into a fixed bed reactor which operates at 70 degrees Celsius and 1 atm of pressure in the presence of a zeolite catalyst. A mixture of acetone, AMS, and phenol is produced and is fed through a pump into the first of two distillation columns. The first distillation column separates acetone and AMS from phenol. The bottom product phenol is then pumped through a heat exchanger where a BPA and phenol stream from section 3 is also fed through. Both streams out of the heat exchanger go into the third section. The top product of the first distillation column is then fed into the second distillation column, where the acetone and AMS are separated into their own streams. The top product is mostly acetone and is fed into a splitter. One stream containing acetone is sent to storage, while the other stream is fed into the fixed bed reactor in the third section. The bottom product is majority AMS and is pumped into a slurry stirred tank reactor, where it reacts with hydrogen in order to form cumene. The cumene produced from the SSSTR is then sent to a splitter along with the top product from the vacuum distillation column in the first section. The cumene that exits the splitter is recycled back into the process, while the other products are sent into a waste stream.
Now moving on to section 3, BPA production. Acetone and phenol are fed into the fixed bed reactor to produce BPA. In the dehydration column, the waste acetone and water are removed from the process as the distillate. The bottom phenol and BPA are fed into the first heat exchanger. The BPA and phenol are fed into the purification column, where phenol is the distillate and BPA is the bottom product. Phenol is fed into the second heat exchanger, which is then fed into the fixed bed reactor. BPA from the purification column is fed, which is then sent to the BPA storage. 20% of our distillate, which is phenol, is recycled, and 80% is purged to avoid accumulation of unwanted products.
Now we go through the simulation decisions part. The Unihoc model is chosen to run our Aspen simulation, and it is suitable for low pressure. Most of our processing units are running at standard atmosphere pressure 1.013 bar. And this model can precisely predict thermodynamic properties for highly non-ideal system at the liquid vapor phase. Finally, it is reliable with exist of polar compounds when the carboxylic acid appear. In our process, many polar chemicals are involved, such as water, acetone, BPA, and so on.
In Aspen, there are 7 models that we can use as a reactor, and we have grouped them into mass balance-based, equilibrium-based, and kinetic-based models. The last two are just not suitable for our simulation because they are too detailed and rigorous, and we just do not have the information we need to model them. So, within the mass-based model, we have our stoic and our yield. We need to specify a conversion for our stoic and yield for our yield. We have chosen to use our stoic throughout the whole simulation because our literature usually specifies reactions in terms of conversion, and it's more convenient to do so. And looking at the separation unit, we have two choices. Within the distillation column, we've chosen to use the STWU because it's a shortcut method with only pressure and recovery specified. The other two units, we just do not have the necessary information. We could also use a separator model, which only required split fraction specified, and we do have that. However, considering that we only have distillation column as a separator in our in our process, we've chose to use the STWU because we believe that will help us in later stage.
We conducted an energy analysis based on the Aspen base case process. Heaters and coolers have been identified as the main areas in the process that consume or generate a significant amount of energy compared to the distillation columns and the reactors. The aim of the heat integration is to reduce the amount of energy and resources used in the production processes while maintaining high quality and efficiency. To do so, we started off by identifying which streams to add to the pinch analysis based on several factors such as the inlet and outlet temperature, as well as the mass flow rates of the streams. 3 hot streams and 3 cold streams are implemented in the pinch analysis. To choose an appropriate value for delta T mean, we took into account cost, space, efficiency, and temperature, and came to the conclusion that 15 degrees Celsius was a suitable value. The cascade diagram is used to show how energy moves from one part of the system to another. Here the pinch point reaches the last interval as heat is being cascaded down through all the intervals. This can be explained by the fact that the duties required by the cold streams are much smaller than the duties possessed by the hot streams. Therefore, the minimum cooling load required would be 44,564 kilowatts and the minimum heating load would be 0. We then designed the heat exchanger network, keeping in mind that heating can only be done above the pinch and cooling below the pinch. The diagram tells us that 2 heat exchangers are to be added to the process, and the streams who didn't reach the requirements would need external utilities. So, 2 heat exchangers have been implemented into Aspen by specifying the heat duties, as it was the value we calculated. By using a heat exchanger, energy can be conserved by transferring heat energy from one hot fluid to a cold fluid rather than simply dissipating it. After heat integration, the total energy consumption has been reduced by 12.1%, and that way we are saving $1.34 million per year, more than the base case process.
There's 2 recycle streams in our process, hence 2 loop and 2 test stream. Looking at the table here, we can see that both loops have converged and the error is minimal. If we look at the errors, a warning, there's 0 error but 54 warnings. 54 seems like a very large number, but upon a closer look, there's only 2 types of them, with boiler or condenser duty being negative. These are ignored because first, they do not impede with the simulation running, and secondly, we have looked at the numbers, and they are all sensible and within the limits specified in literature. Therefore, we have chosen to ignore them because they should not matter at this stage. This is the end of our presentation. Thank you for listening.